So in the last class, under the crystal, we learned about what we call the crystal system, Bravais lattice system, and so on. And then we learned about the cubic system. We focus on cubic system. Under cubic system, you know we have a simple cubic, we have also a body center cubic, and also the face center cubic. So this is what we learned in the previous class. We learn also we can know the APF. APF stand for atomic packing factor. Atomic packing factor, which is basically just simply what we call the volume of atom. Volume of atom in unit cell. In unit cell divided by the volume of the unit cell itself. Volume of unit cell itself. Okay, so we know that from when I show the calculation for the simple cubic. So in the simple cubic, the APF for the simple cubic is around 68%. Okay, for the body center cubic, the APC, the APF, not APC, APF is around APF. Let me change the thing. The APF is 74. PCC, no, this is simple cubic, is not that. The simple cubic APF is around 52%. So for the BCC is around 68%. And lastly, we learn about the FCC. The APF for that is around 74%. Okay, I show you during the class how to calculate for the atomic packing factor for the simple cubic. Okay, so let's do for a while how to do for this BCC. Okay, so let's do some calculation on the BCC. How to find the APF, atomic packing factor, for the body center cubic. So in order to do that, we need to, as usual, is a cubic. So meaning that you need to draw like a cube like this. Okay, like a cube. And we know for the what we call for the body center cubic, there will be what we call the atom will be here, will be here, here, at each corner. But then in the middle, there are also atom in the middle there, So that is basically body center cubic. And the atom here, when we talk about calculating the atomic packing factor, we need to make sure that this atom is not simply a dot. We need to sort of like make it bigger and bigger and bigger. So if you look in the what we call in the 3D thing, so you will see something like this, something like this. So that is basically how it's look, the body center cubic. How to move this thing? Okay, so this body center cubic. Okay, so this is basically what one of your friend did. Nabil. He draw this thing and in the fusion. So I asked some of whoever want to extra mark do this thing. So some of you, they sort of like do that thing. If you see from this image, you can see this atom. The important thing here, the atom must be of the same size. Okay, this atom, the middle, is of the same size of this atom on the corner. Okay, and also the atom must, if you look here from here, how to change the, okay, if you look from the front, you can see the corner atom doesn't touch another corner atom. So this corner atom doesn't touch this corner atom, this corner atom doesn't touch this corner atom. But this corner atom, they touch the middle atom. However, if I make it bigger, if you look here, if I make it bigger, okay, you can see Nabil, your friend, from the outside, it seems correct. But then when you go, what we call go zoom in, you can see there are sort of empty space there, empty space between this and this atom, the center atom and the what we call the corner atom, which is not right lah, because the bonding happen when the atom sort of like connect with another atom. In body center cubic, the what we call the side atom must connect with the center atom. So this is what I draw. Okay, if you look here, this is the correct one. If you look here, there are no sort of like how to this thing, it's difficult. Wait. Okay, so you can see there are sort of like no gap there. Okay, so the atom is connected. The corner atom is connected with the body atom, the center atom. Why this is important? Okay, why this connectivity is important is because when you try to cut this in the in the plane, let's say I cut like this. Let's say I cut like this. I cut in the diagonal, and then I try to inspect the the section analysis. Okay, so what you can see here, from here you can see that wait, let me make bigger a little bit. Okay, so this myself go up. Okay, so you can see this is the important, because if this atom, the corner atom, doesn't sort of like connect with the center atom, then you cannot sort of like correlate the radius of the atom with the cubic length. Because by correlating the radius of the atom, we can sort of like know by correlating the radius of the atom with the length of the unit cell, you can get the APF. Why I say that is because like this. If let's say in this thing, let's say I make it like the image just now. Let's say I make like I draw this thing. Let's say I draw like this. Okay, I draw like this, I draw like this, I draw like this, and then I draw like this, and then if you want to find the APF, atomic packing factor, what you do is that you need to find the volume of the atom and also divide by the volume of the unit cell. Okay, let's say you will give this length as A. Let's say this is A. Okay, so we know the volume of the unit cell. The volume of the unit cell is basically A3 lah. Okay, the unit cell, because the cube, the volume for the cube is the cube lah, A to the power of 3. So that's fine. So the volume of the atom. So for the volume of the atom, first you need to know first how to calculate the volume of atom. Because we use, if you look in our design before, we use the sphere. Okay, we use the sphere. So the sphere have the volume of the sphere. The volume is basically 4/3 pi r3. So this is the volume of the sphere. And if you look at this image, for this simple cubic, let me close this first. Let me close this thing first. Let me cancel. Okay, if you look here, if you look at the image here, let me remove this thing first. Okay, if you look image here, the unit cell is like a cube. Okay, so now we need to know how many atoms inside the cube. We can know for sure there are one atom there, and also another atom, because this corner cube, if you sort of like combine them together, you get another one atom, another one sphere lah. This corner add with this corner, add with this corner, add with this corner, add with this corner, and so on, you get another atom. So in BCC, this is body center cubic, you have two atoms inside the unit cell. Okay, so you have two atoms inside the unit cell. So meaning that in BCC you have two atom, which is sphere in dimension. So you can basically do 2 times. Let me put different color lah. So basically, because you have 2 atom here, so you have 2, and then you time with the the volume of the atom, 4/3 pi r3. Okay. Okay, so you you get that. Okay, so this is basically the sphere volume. 2 is basically the number of atom. A3 is basically the what we call the volume for the unit cell itself. Okay. Okay. The thing is, when you do this like this, you cannot really sort of like cancel out the R and A. The problem here, because you have R and also you have A. Okay. In order to get the value in terms of numbers, okay, in terms of numbers, you need to make sure the R correlate with A, because here at the end of the day you have something R over A, which is not a numbers. Okay. We know pi is a numbers. Pi is 3.142 blah 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 blah. 4/3 and 2 is also a numbers. That's okay. But now the A and R is not a number. Okay. So we, in order to sort of like cancel out this together, we need to correlate A with the R. Okay. With the what we call in the previous class, in the physical class last time, we do for the what I call simple cubic. For simple cubic, it's easy, because if you look at the cube here, the simple cubic is quite easy, because the simple cubic is like this. So you can see something like this, right, in the simple cubic. Okay, this is in simple cubic that we learned last class. So example of simple cubic in 3D is where is simple cubic. Let me find simple cubic. Okay, so this is simple cubic. Wait for it. Okay, so this is simple cubic. If you look at the front, you can see the length here. The length for the what we call for the one length for the cube here is equivalent to 2 radius, because this is the radius for the atom 1, this atom 1, this atom 2. So you can have the A equivalent to 2R. So that's easy lah. That's easy. How to remove this thing? Wait, okay, like this. Okay, so for this we can correlate what we call, we can correlate the A with the R. So you can say that the length here, so this is A, so the A equivalent to 2R, because the radius of the what we call of the atom inside the simple cubic. But for the BCC is a little bit different. If you look at the BCC now, BCC, if I draw like this, okay, if you look at the what we call this thing, this crystal for the BCC, this atom, this corner atom doesn't touch the another corner atom. So it means that you have something like this, you have something like this, you have something like this, and then you have something like this, you have something like this, and then in the middle you have another one lah. You have another one in the middle. But remember, this thing.
Assalamualaikum, sir.
Yes.
Sir, I will be joining this meeting with Ikram.
It's okay, it's okay. Later you tell me lah. Okay, so if you look here, the A here, the what we call the length of the cube, you cannot correlate with the R here, because this what we call, this is R. Let me show here. Let me put in the black. So this is R, the radius. This is the radius. Okay, this is the radius. We cannot say this because if you look in the face here, it's not, you cannot just say this R and then this R and then this R and then this R. You cannot say like this. The reason why you cannot say like this is because if you look at the what we call the simple cubic from the front, let's say I put in the front, this what we call this center is not exactly on the face of the what we call on the face of the thing. So it's inside. So if you look here, the image here is not actually like this, but rather something like this. Let me draw at the bottom lah. The bottom, the image somehow like this. Okay, and then I draw like this. You have something like this, and then 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 you have another what we call another sphere inside there. Okay, inside in the middle. So you cannot really find what is correlation with A with R at the moment lah. At the moment, you cannot just say that A is equivalent to what R. You just know that at this moment, at this moment, you just know that R is less than A. The radius for the what we call for the atom here is less than A. That's all you can know. But you don't know like the simple cubic, you know that A is equivalent to 2R because all at the edge. But here, you don't know how much smaller this R. So in order to know that, you need to find the ways to correlate lah. So how you do it is basically like this. So if let's say I take this is a cube. Let's say this is cube. Okay. This is the cube. And then if you look at this image, let me open the image first. If you look at this image, let me put like this. Okay, and then I make the plane. Let me draw like this, and then I cut it. I inspect the section analysis. Okay, okay. So if you look here you can see at the middle in the diagonal, this you can correlate. You can have this because this is touching. That's the important reason why they are touching is important here. So you can have this R radius here, and this is basically in the middle is basically 2R, and this another R. So effectively, what you have is basically from here. Let's say I give the what we call the notation. Let's say this O origin, and then this A, and then this is B, and then this is C. So we know from O to A is basically OA is basically 4R. 4R. Why 4R? Is because of this. You can see there are 1, 2. From here to the center, and then from the center to the edge, there are 3, and then another one here. So they are like 4R lah, 4R. So you need to see from this lah. You need to see from this is not really clean image, but basically it will dead center lah. It will dead center here. So you have 4R there. Okay. So now you have this OA is 4R. Okay, and you know from A to B here, this one. This A, this is 4R. So AB equivalent to A. Okay, so you have 4R, you have A. But now we want to correlate 4R, the R and A, the radius and also the length. For time being, we cannot do that. So what we can do is that we make like another line from O to B. So O to B is basically what? Okay, if you look here, if you look, because O to B is at the bottom, at the bottom there. If you look here, this is like the what we call the triangle, the right triangle, because this is basically the what we call the right triangle lah. So we know the right triangle is that the formula is from the Pythagoras. We can say that BC squared plus OC squared equivalent to OB squared. Okay, and we know the BC, we know how much here because this is A and this is A. So we can say that A squared plus A squared equal to OB squared. Not OB OB lah, equal to OB, not OB squared lah here in this case, because the OB is we want to find what is OB. So OB here. So we can say now the OB here, this OB, the OB is basically 2A squared. Okay, so now we have three things. We have OA, we have AB, and we have OB. Okay, we have that 2A squared. So now we want to okay, so 2A squared. Okay, so now OA, OB, so this one OA, and then AB, this one, and then OB is basically the right triangle also, because you can make the right triangle here. So we know again the formula for that. Let me make it smaller a little bit, okay, so that you can see. So again we use Pythagoras theorem. So we got what we call OA. We want to see this one, the one in the yellow. I draw in the yellow. So basically the Pythagoras for this yellow thing is basically what? It's basically basically OA squared equivalent to AB squared plus OB squared. So that's basically the thing. And we know what is OA. We know OA is basically now 4R. we just take whatever here. And then AB here, AB is basically what is AB? A. So A squared. Okay, and then plus OB. So we know OB is 2A squared lah. 2A squared. So we put 2A squared and then square lah. Okay, because this Pythagoras theorem. So OA is basically 4R squared like that. Okay, and then you get, when you solve this thing, what you got is basically 4 times 4 to the power of 2 is 16. 16R2 equivalent to A squared plus this is 4 A squared lah. 4A squared. Okay, so you are basically plus ke 4A squared A squared, so 16R, yeah, like that lah. Okay, so let me check. A squared plus 2A squared. No, OB is there. Oh, OB is already there. OB, no, this OB, A squared plus OB squared. So this is basically already OB squared lah. Let me put here. It's already OB squared. So OB squared is basically 2A2. So this should be just 2A here, 2A2 here. So basically 2A2 here. So now it's basically 16R plus 3A2. 3A2. So you can make it 2A2. 2A2. So what you get now is basically 16R squared equivalent to 3A2. And then now you can sort of like correlate lah. So A2, let's say you want to make from A perspective, A2 equivalent to 16 over 16R2 over 3. Okay, and then let's say you want to get the A equivalent to square root of 16R2 over 3. So it's also same as 4, and then this R over 4R over 3. Okay, so now basically you are successfully relate the A, the length of the unit cell, with the R. So this is how what I mean by relating the A to R. So you know that the length of the A is equivalent with the 4R over 3 squared. Okay. Okay, so when you have all this thing, then it's easy now to use this correlation. So this thing. So let me copy this thing, APF for BCC here. Let me copy, Ctrl C there, and then I put bottom here. Let me put Ctrl V. So let me bring this thing in there. I bring this nearby. Okay. So now once we got this correlation A and R, then we can calculate lah. So 2 times 4 over 3 pi R3, and now because we already know what is A, we can just put 4R over square root 3 to the power of 3. So that's, and when you do like this, you can cancel out this thing lah. So you can have this 14. This is basically 8 over 3 pi R3 divided by this 4 times 3 is 64. 64. 4 times 3 64. 64. 64 R3 over power root of 3 and 3. So here you can see that you can cancel out the R and the R. Okay, so now you left with everything is just a number. 8 is number, 3 is number, pi is a number, 3.142, 64 is a number, this is number, this is number. So when you put this in the calculator, then you will get the value of 68%. Okay, so this 68% is basically the atomic packing factor for the what we call for the BCC, body center cubic. Okay, so that's how you find the APF for the BCC. Okay, for the FCC, so phase center cubic, let's do for the phase center cubic. This quite easy lah. Phase center cubic is easier because if you look at the image of the phase center cubic, let me go for this image. Let's go to the phase center cubic. Okay, let me go for the phase center cubic. Okay, so this let me it open first. Okay, so this is base center cubic that we learned before. So if you look at the what we call in the edge, you can see still the corner doesn't touch another corner. This corner doesn't touch this corner, this corner doesn't touch this corner, but they are atom in the middle, right in the middle. And here you can use straight away here, because you can see from here this what we call this corner to this bottom corner, you can make like a pass. They are connected here, this connected to this the atom in the face center plane, and connected to this center corner atom. So you can have this R, and then another R in the middle here, another R here from center to the edge, and then another R to the corner this. So now, because it's easy, so it is easier to calculate lah. So now you have something like this, and then you have something like this, and then you have in the middle like this. Okay, so we know now this thing connected with this, and then this in the middle connected and connected. So you have this 1R, 2R, 3R, 4R. So you can, and this what we call this thing is the length is A. This length, because it's cube, is A. So we know this thing is R, 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 R. So now we can see clearly that from this what we call from this triangle, we can say that this triangle, this is 4R, and then this A and this A. Okay, so that make it easy lah, because for example the Pythagoras again, so A squared plus A squared equivalent to 4R squared, so giving you 2A squared, this 4, 2 is 16R squared lah. So then you can correlate A equivalent to A squared equivalent to 16R squared over 2, and then making A equivalent to square root of 16R squared over 2. You basically get this is not 2A. So this is wait 2A 16R A squared equivalent to, okay, so this you can cancel lah, because this basically cancel, you get 8 lah. So you get A squared over 8R2 lah, 8R2, and then so because this R2 is under the what we call square root, you can get square root 8 R lah. So you can get the correlation A equivalent to 8R, square root R. So this is correlation for the FCC, face center cubic. Okay, so when you have this correlation, then you can find the APF. So you know the APF, the calculation of APF is this. Let me copy this again, Control C, and then we go bottom. Let me put here, Control V. So you get this thing. So for the APF, for the what we call for the face center cubic, let me put face center cubic, APF for face center cubic, we need to sort of like find what is this amount, the number of the atom inside that, inside this unit cell lah. So if you look at this image here, you can see from here, for this unit cell you have 1, which is this, the top one, and the side this one, and then this, and also at the what we call at here 2, there are 2, and then there are 3 atom here. This is the third one, and then the corner make 1 atom. So you have in effect you have 4 atom inside the unit cell for the FCC. So you are basically, you just change lah this thing, instead of 2 you change into 4 lah, into 4. Okay, so when you do like this 4, and then you already know the A is basically square root of 8R. So you can get now 4 times 4 is 16 over 3 pi R3 over A cube. So A is square root of 8R and then cube. Okay, so when you do like this, you know that you can cancel R, you can cancel R, and then again you left with this numbers, and numbers. So when you do all this calculation, you will end up with 74%. So APF, atomic packing factor, for what we call for the phase center cubic is 74%, and this is how you calculate lah. So we have learned how to sort of like calculate the atomic packing factor for the FCC and BCC, and also simple cubic in the last class. So if you look here, the SC, the simple cubic, have 52, and the example of simple cubic is polonium. BCC, example for the BCC is iron. Example for FCC is gold. Example of gold. Okay, if you look here, if you look at this, you can see most of it is metal. In fact, what we call in fact, when we doing this, what we call doing this calculation for the APF, what we do is that we use, when we do APF just now, calculation of the APF, we use first the same size sphere. What does it mean is that same size sphere is mean that the same element lah, same element, because if the different element, different size, so meaning that this is same element. So that's why the what we call the metal, what we see now, we have metal lah, metal, because metal, they are bonded using what we call the bonding in metal is metallic bonding. We have learned this metallic bonding before. So this is how metal sort of like bond in the structure of the crystal. So that is same size sphere. Okay, in fact, for the metal, most metal, they are basically is cubic system. Is either simple cubic, body center cubic, and also face center cubic. And also metal also have hexagonal close packing. So when we talk about the metal, this is the sort of like common crystal structure lah for the metal. The most common one is this thing, body center cubic, face center cubic, and hexagonal close packing. For this simple cubic, there are only one, which is polonium, because we have learned before that simple cubic is not stable, and also the atomic packing factor also is very less, it's not efficient packing. So if you look here, if you look at the periodic table, if I periodic table crystal structure, so let's go to the what we call crystal structure, periodic table for the crystal structure. If you open this, okay, you can see now the metal is basically here lah. We know that metal make up most of the thing in the periodic table. So if you look here, the BCC, the yellow one is the body center cubic, the pink one is the hexagonal close packing, and what we call this is FCC, face center cubic. So you can see until here, most of the metal is basically either FCC, hexagonal close packing, body center cubic, and some metal is polonium, is simple cubic lah, simple cubic. This is rare lah. So that's why when we talk about the cubic system, when we talk about metal, more often than not, you will face BCC, you will face FCC and hexagonal close packing. We will not touch about the hexagonal close packing, but how to calculate that thing you can do yourself lah. But basically I just want to stress that for the metal, these three is common: BCC, FCC, and hexagonal close packing. Hexagonal close packing. Okay, so that is about the cubic system for metal. Okay, sometime when you see, let me make like this. Okay, So let's say we take diamond for example, diamond for example. We know diamond is made up from the carbon, and all inside the diamond is carbon, okay? And carbon, because all is made of carbon, then the size of sphere is similar. So let's look diamond structure. So we open the west star, and then we sort of like we open the diamond. Let me open the diamond. Where is diamond? Okay, so the diamond have this structure. You can see the diamond have this structure. How to do this? Okay, so diamond have this structure. So you can see this, what we call the cube. You can see there are a cube there. So when we talk about unit cell, we talk about something inside the unit cell lah. The unit cell here is a cube. So they are, in order to make life easy, let me remove whatever not inside the cube. Okay, let me remove whatever not inside the cube. So I take this, I just remove this, remove what not inside the cube, remove. Okay, I just remove the thing. Let me see from this angle. So I remove, and then I see from this angle. Okay, it's done. Okay, so now this is what the image of diamond. Let me change this thing. The image of diamond. So if you look here, we know this cube mean is a cubic, but this is what? Is it FCC? Is it BCC? Or is it simple cubic or what? Because there are no something like this in what we call the 14 Bravais lattice. Because when we learned in the previous class, the Bravais lattice, let me recall a little bit. Bravais lattice. This is what we learned in the last class. Bravais lattice. Take Wikipedia. We said in the previous class that for a crystalline material, they have sort of like seven crystal system, which is triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, and cubic. Okay, so you have 1 cubic, 2, 3, 4, 5, 6, 7. So there are 7 crystal system. Okay, and within the 7, there are 14 Bravais lattice. We focus just now only on cubic. Okay, cubic. So you can see for the cubic, they have the what we call this one, and also this body center cubic. You can see there are center there, and this is the face center cubic. Okay, face center cubic. So they are nothing something like this. So you can see here, they are nothing like a diamond. So diamond is what? So if you look closely, this diamond is made up of FCC. You can see they are on the edge here, they are atom here. So let me show you this atom. They are atom here. They are atom here in the, how to make it? How to make? I don't know how to use this. How to select? No. But you can see from here you can see that this is FCC. They are FCC because here they are in the side, and here they are in the side. Here they are atom on the edge lah, on the edge, on the face. They are atom on the face. If you look like this, they are also atom in the face, and also they are atom at the face. But they are also atom inside. They are also another atom inside, which is not in the face. They are another atom inside. So this what you see just now is basically non-primitive. So what you see just now is non-primitive unit cell. Okay, what is non-primitive unit cell? We need to compare first with the primitive unit cell. Primitive unit cell is basically the cell in this 14 Bravais lattice lah. So this what you see here. So this is primitive unit cell. So this primitive unit cell is like the base of all the 7 crystal structure lah. So the cube, the primitive is this. Okay, so when you add something inside, they are what we call it non-primitive lah, non-primitive. Okay, non-primitive. So this is basically a non-primitive for simple cubic like this lah. So for this diamond here, they have what we call let me do like this. Okay, you have this thing, this what we call this extra atom inside. Okay, so this mean is a non-primitive lah, non-primitive unit cell. Okay, non-primitive unit cell. So you might ask, okay, then why is this cubic? Is this FCC or what? It is still face center cubic because this what we call this this what we call this this atom inside this cube can become a corner for another cube. Okay, because if I make it bigger, let's say I make it bigger here, maybe I make it 3, 3, 3. If I make it bigger, this thing can be the corner of the, because it's, remember, it's a repeating unit, it's the same pattern, and then you just shift the pattern at the angle, so you can still get the repeating pattern again. Okay, so this we call it diamond, we call it cubic system, and it's under FCC, face center cubic. And the reason why in the middle there they are what we call, they are extra atom doesn't really matter, because if you use this as a corner instead of this, let's say this, now this is corner, but if you use this as the corner instead of this, then you still get the face center cubic again. It's just like the unit cell within the unit cell. So it's the same thing, it's just the way where you choose the corner. So if you choose this corner, you can still get something like this. So that's why, even though this is not inside the what we call inside this simple this cube body center or face center, or this, there are no structure of that diamond inside this 3 cubic system. But this thing, if you move this to the corner, if you make this to the corner, you will get the same thing again. So it's basically a redundancy. So that's why this diamond, even though it look complicated, but it's still a face cubic center, face cubic center. Okay, so that's the thing. So similarly, if you look like the so that's diamond. So diamond is they use non-primitive unit cell. Okay, but you see diamond here, all the sphere is the same size because the carbon, all is carbon. But if you look for the what we call, let's say we take the example for the salt. This is rock salt, rock salt, the table salt that you use in the kitchen lah. So table salt, they have 2 different atoms, the Na, the sodium, and also the chlorine, the sodium and chlorine. So then if I go and find the what we call open the rock salt. Okay, open the rock salt. You get something like this, Okay, let me remove the extra, because we want the cube only. So let me remove the extra plane. So I take this and I remove this, remove, and then let me make this thing, remove. Okay, and then now you can see now this structure, the structure for this salt, the garam is basically FCC also. Okay, if you look here, they are the face, the what we call this the I don't know, this is what, this is carbon or chlorine, the sodium or the chlorine, either one lah, chlorine or sodium. Let me check. Chlorine is bigger, so if you want to know which one is chlorine, which one is the sodium, just look at the periodic table, which one is bigger lah. So for example, let's say I took the PT table there, PT table, and then we see the difference between the chlorine and the sodium in terms of size. In terms of size, let's go to the size. Where is the radius? Let's say take the radius. Take the radius. So we can see the chlorine is around, this is sodium is here, the atomic number of 11, and the chlorine atomic number of 17. Okay, so meaning that because this have a higher atomic number, is bigger lah. I mean, because this is still on the top, so this chlorine is bigger than sodium. So the chlorine is the chlorine is the yellow one lah. The sodium is this the what we call this green one. So let me check, is it correct or not? Let me check this. And then how to check this thing? View object properties atoms. I don't know how to view this thing, but okay. So you can see the sodium, or so the other way around. Sodium is in the what we call the yellow color. The gold color is sodium. So you can see the radius is around this big. I mean, this is just the software they give the thing. And the chlorine is the green one. The chlorine is the green one. Okay. Yeah, because the size in terms of size. Yeah, if you look here, the color, because I put this radius. Radius. We learn in the what we call in the atomic the periodic table just in the previous class, that the size for the atom become bigger when you go from the right to the left. From the right to the left. Okay, so you can see here the color for the chlorine here is less blue, right, compared to the sodium. So sodium here, because the color is darker, if you look here, the color here, the maximum, and because we are in the radius here, so from here we can see that the sodium is bigger than the chlorine. Okay, so that's why this bigger one is basically the sodium lah, the sodium, and this the gold one, the gold one is a sodium, and the green one is the chlorine. Okay, that's the idea lah. But if you look here, okay, if you look how to this, okay, if you look here, you can see that this is FCC. Because why? You can see the I just say the gold and green lah. The gold atom make the FCC, and you can see inside this FCC you can also have the green. But remember, if you make this green here, this green as a corner, as the corner for this, instead of this thing, you switch the part, mean that you take another one, then you can have the FCC again for the what we call the same thing but different corner lah. So you can make this is the FCC lah, because even though they have something in the middle, in the edge here, but because it's repeat again and again, it's like you have a unit cell, and also you can make also unit cell from here. As this a corner, you can expand further lah. So that is basically the reason why if you see something complicated like this, it still can be FCC or BCC, because whatever inside it will repeat. You can just change the thing like a diamond, even though it seems like difficult to see FCC or not because of this internal atom, but if you can move that atom to become a corner, then you can still get the FCC structure, FCC cubic structure. Okay, so that's the thing about the what we call this thing. Let me show here. So we can see now. So we know now about primitive unit cell and non-primitive unit cell. Okay, so now once you get this knowledge about the APF, the atomic packing factor, and also whether the thing is primitive or non-primitive, you can know the reason. You can know the usage lah scientists use, because we know that SCP, hexagonal close packing, have the atomic packing factor equivalent to the FCC, and this FCC have higher atomic packing than the BCC, and then BCC have higher atomic packing than the SC. Okay, so the atomic packing for SCP, I repeat again, is around 74%. FCC is around 74% in terms of atomic packing, atomic packing factor, and BCC is around 68%, and simple cubic have 52%. Okay, the atomic packing factor here allow the scientists sort of like compute the theoretical density. Because atomic packing factor, what does it mean? It's just how dense is the system. Because if there is a lot more percentage covered of atom covered inside the unit cell, then it's more denser lah. So we can say that in terms of density, this is denser, and this is less dense. Okay, so we know that the example of FCC here is basically the gold. We will learn before. The example of the what we call for the BCC before we learn is iron. Okay, so because the gold have what we call the atomic packing factor of 74%, and iron have the atomic packing factor of 68%, we can say in terms of density, theoretical density, the gold is denser than iron. So if you look in the Wikipedia, if you go here and if you try to sort of like put this gold, let's say gold density, what you get 19, okay, 19.73. so let me put here. So the density for the gold is basically 19, I just put 19 lah, 19.7 cm3 over gram. And for the iron, let me put for the iron, let me find the iron, 1943 iron. Okay, iron density is 7.8 7.8. So this is 19.3, and then the iron, so this gold, and for the iron is 7.8 like that, cm3 over silap ni, gram per cm3, it's other way around. This is gram over cm3, and then this gram over cm3. Okay, so you can see now the gold is denser than iron because of what? Because of its internal structure. Because gold have this FCC crystal system compared to the iron, which is body-centered system. Okay, but the gold here, if you look the gold, if you have ever touched gold or whatever, we know that in terms of like what you call, we know that gold is softer, right? Gold is softer than iron. Okay, remember, something dense doesn't mean it is hard. Okay, dense material is hard, but then there are many things that contribute to the hardness of the material. For example, here, even though gold have higher density than the iron, but the gold is softer than iron. The word softer here, what is the meaning of the softer in material science is basically the ability to move lah. You can sort of like bend the gold is much easier than you bend the iron. Okay, the reason why gold is softer than iron is due to something what we call the slip the slip plane. Okay, the slip plane. Okay, the reason why gold is softer than iron is because of the slip plane. And in this case, we need to understand what is plane. What is plane? Plane is just simply, it's just plane lah. For example, let's say I have this cube. This is plane. Okay, that is plane. This also a plane. I mean the plane is just like a layer lah, like a layer where the atom ni lah, where the atom sort of like reside. Okay, so the plane, we can say the plane is just simply a flat surface lah, flat surface, or sort of like layer lah, layer like that. So that's a plane. Okay, so let's talk a little bit about the plane. Okay, if you sort of like okay, let's say I go for the goal. Let's say we go for the goal. File, open, and then find goal. Where is goal? Okay, there is goal. Okay, let's see, there is goal. Okay, so this is goal. Okay, so this is goal. Okay, the plane is basically the, for example, let's say I'll make it bigger lah, boundary. Let me make it bigger. 3, 3, 3. Okay, you make a bigger like this. Okay, okay, okay. boundary. This 3 also. Okay. So you get something like this. So the plane, for example, let's say I put this edit, let's say lattice plane, and then I make it 100. Let me lattice plane new. Let me put 100. Put 100. Okay. So now, you can see like that. They are like a plane. Okay, a plane. So that is plane. That's what we call the plane. Plane. So if you look here, when I click here, you can see they are sort of like the numbers 100. So this is what we call the Miller index. Okay, let me put here. So this is the plane. So we know inside the cube, let's say we talk about the cubic system. Inside the cube like this, you have this is A. And let's say we put in the coordinate system. This is X, this is Y, and this is Z. Let's say we want to describe this plane. Okay, X, Y, Z, as we learned before, X, Y, Z is simply coordinate axis. Okay, coordinate axis. Okay, so in order to describe this, what we call the plane, what is the number for this plane, you need to use the ABC. ABC is like length. So if I put here, this is A, the length from here to here, from cube, this is A, the length from here to here, this is B, and the length from here to here, the cube itself, is C. Okay, so if you look at this plane, which is in the front of the cube, you can know that from the X or A, he have his length from A, let's say I put A, he got length of 1. Let's say this, we put it like this lah. Let's say we put 1 lah as a unit lah. Unit 1 in terms of length. So A is 1 because the what we call the sort of like the length, the distance from the origin to the A here is 1 unit. Okay, 1 unit. Okay, now we want to see what is B. So the B, if we want to see the distance from the origin doesn't touch the B. Okay, doesn't touch the B at all. So you cannot really know what is the what we call, we don't know the distance from the origin to B. So we can say in this case, when you face something like this, we can say B is in the infinity lah, because you cannot sort of, the origin here will not ever touch the B. So we can say the B is at infinity lah, infinity distance from the origin. So that's why B is negative, because you cannot calculate, because the origin so the origin is here. When I say origin is here, this is the origin. Okay, so because B doesn't touch the origin, there are no like sort of like the path to the B, then we can say B is infinity lah. And also same with the C. Okay, if you look at the C here, okay, C is basically the height, because the origin doesn't touch the height here, the height for this. Okay, it doesn't really sort of like, it doesn't what we call, it doesn't meet the height of this plane that we sort of like shade with the red here in the front. So C is what we call infinity lah. So the number that you see just now 100 is basically, we call it Miller index. Okay, Miller index, how to calculate the Miller index is just to take the reciprocal, So reciprocal means that you make a bracket like this, 1 over 1, and then 1 over infinity, and then 1 over infinity. You get something like this. So this is for A, when we talk about Miller index, we talk about the HKL. HKL. They just the term. This is ABC. This is HKL. So when you see HKL, it's basically it's already reciprocated. So this is basically come, the one in blue here. When the one that I circled in blue is basically come from the in this ABC lah. So you take the reciprocal for this, what you get is basically 1, 0, because 1 over infinity is 0, 0. That's why you get something like this. 100 is basically there. Okay, 100 is basically there, the plane. Okay, so if let's say if I want to make like, if let's say just another example, let's say I have something like this, and then I want to describe this thing. So let's say I have this one point, and then I also have this is from the X, so this is the A, and then let's say I want to make it like B, so this B, right? So you have this point, so this B, and then this C. So you have you put the point in the end of the unit cell of A, B, C, and then you will end up with the what we call with the plane like this. Okay, so you will end up with a plane like this. So this, if you try to put in terms of A, B, C, you know that A is 1, because from the origin to this what we call to this atom or to the edge is basically 1 unit, and then this 1 unit, let me put in the yellow, 1 unit, so I put in yellow, and then from this origin to the B is also 1 unit, so B also 1, so B also 1, and then from this origin to the C, so the C here in the blue here, so C also 1. So then when you take the reciprocal in terms of the Miller index, you make this bracket, and then 1 over 1, 1 over 1, 1 over 1. So the Miller index is 1, 1, 1. So you can see sort of like the what we call this triangle is 1 over 1. So if I go here and if I try to make edit and go to lattice plane, and then let's say I remove this clear, and then instead of 0, 0, 0, I put 1, 1, 1. Okay, enter. Okay, so you get something like that. Okay, you get something like that, something like that. So you can see something like that. Okay, something like what we call the triangle, the triangle. Okay, the triangle. Okay, 1, 1, 1, like that, triangle. And then actually it much clearer if you use this boundary is 1, 1, 1, 1, because this big. So let me apply. So okay, let me put like this, so like that. So you can see this is imagine this is origin. Okay, let's say this A, so you can see there that thing. Okay, so this is into body center. Okay, because the plane is where the what we call the atom reside, where the atom reside, not in just in the what we call, if you put in the sort of like in the empty space here, then that's not plane lah, because it's just nothing there. So that's so I think I can just put like this, object, edit, that is plane, and then this is, let's say this is distant 1. Okay, edit, that is plane, new, this is 100, so that is 100. Let me put here in green. Okay, so you can see the green one is the plane of 100, 100, whereas the what we call 100, let me put A here. Okay, you can see like that. Okay, so this 100 is in the front. So imagine the what I call the origin is over there, in the this origin. Okay, So it's the same as what we mentioned before. This is 1 1 1. Why the structure like that? Is it same or not? Is it same or not? That go hujung. Let me check. This, if you go here, that is the way around. Yeah, but I think this thing you can just sort of like, you just go here, plane Miller indice calculator. You can just find the way lah if you want to what we call to dig further lah about this. Is that you just go draw that thing. So you can see here, much easier lah. So 111, if you want to have Miller indice of 111, you can see like this. Okay, so this, there are 1 here, 1 to the x, 1 to the y, 1 to the z. If you go to 100 here, 100, if you view, you get something like that, because the 1 here is basically from the origin to the x. From the x, so the what I call the length from the origin to x is 1, so 1 unit. So that y here, and 00 here is because this origin doesn't sort of like plane does not it doesn't meet on the x and y lah, y and z. So you can just try to play 2, 3, whatever. You can just you can just learn from here. That's, I will not discuss in further detail lah, but basically what I say is that they are plane lah. That's what does it mean by plane. That's what I want to say lah. So the reason why gold is softer than the iron is that they are, it's much easier for the plane in the gold to slide compared to the iron. Okay, the plane in the gold is much easier. For example, let's say I see gold here. Let's say I make it 3. Let's say I make it instead of 1, let me put 3, 3, 3, 3. Apply. Okay, let me I remove the. Okay, so that is 111. So from here, if you look from what we call from this, you cannot really see how they are actually in the space. If you click the space filling, you can see something like this. Something like this. So where is the plane just now? So the plane is there. The plane is there. The plane is there. Okay. So in the gold, I think much easier like this. I think much easier if I open unit cell visualizer. Unit cell visualizer. And then let me click here. Okay, so gold is FCC. Gold is FCC. Okay, let's say put layer. What's the thing? Okay, so you can see this triangle. That is basically 111. If you remember just now, this is 111. Okay, so if you try to see like this, this triangle, the triangle that we see in the Vesta just now, this triangle you cannot see here. Let me put important stick. This triangle is equivalent to sort of like this thing. You see the triangle there? The triangle, this is the plane. So the plane. So in gold, why gold is ductile, gold is sort of like softer than the iron, is because they are slip plane. It's much easier for this plane, let's say this red plane, to slide like that. It's much easier to slide against the what we call this kelabu, this grey. And this grey is easier to slide because it's easier to slide because this face center cubic have this close packing structure. Okay, let me explain a little bit about what is close packing structure. Close packing structure is that if you look here, if I go to this, let's say I go edit, go to the file, open. Let's say I take polonium. Okay, okay, polonium, you see like this. And then if I make a space filling, and then I make a lot more, I make it 3 3 3 3 3 3, apply. So you can see something like this. You can see, if you see from the front, they are whole. Okay, so meaning that it's not close pack. Okay, so this polonium is simple cubic. If you look body, if I take open, and iron is body center cubic. Iron, okay, so iron is example for body center cubic. Let's say I take it a lot more. I make it more. 3 3 3, apply. Okay, so you get something like this. And then if I make a space filling and I see it from the front, you can see there are still hole there. You can see there are hole here, hole here, hole here. So it's not dense. It's not dense. But if I go to the what we call to go FCC, open. FCC is example of FCC is the gold. Okay, open. Okay, and I make it a lot more. I make it 3 3 and 3, apply. And then you can see something like this. Okay, and then I make it I see from the front. Okay, and then I make it space filling. You can see here, compared to the iron, you have hole. Gold, they don't have hole. This is what we call close pack. This is what we call close packing. Close packing. Let me put here. This is close packing. Close packing. Close packing. The idea is something like this lah. Let me open just for a while. Give me another 3 minutes like that before we end, because I want to explain about this close packing a little bit. Okay, close packing takes time to open. Okay. Let me escape. Okay, let me okay, let's say this. If I don't know how to make this thing. Okay, let's say this. So imagine this circle is basically the what we call how to this thing. Let me put here lah. Let me make like this. Okay, let me, because the thing goes here. I don't know why it shows in the another monitor. But anyway, let me close this thing first. Okay, so if you look here in this okay, in this here, if you put this is, imagine this atom, you stack like this, you put this at the bottom layer, so you can see there are hole here, the red and the green hole, the red and green hole. If the second layer you add, let's say you add the close packing, meaning that it try to sort of like fill in the hole. Let's say this you put on top of this thing, the red thing you put on top of the hole of the red. When you put on hole on the red, you can see this green is still not close. Okay, close packing. So the third layer, okay, you can see the distinction between FCC and SCP. So the third layer you can put to cover this what we call this hole, this what we call the green hole. Okay, the green hole like this. So if imagine there are another layer, you can put that layer on top of the green hole, mean that there are another atom here. So that is basically what is this shows. So you can see here. So you can see that the first here, I don't know how to make it bigger. Okay, so you can see at the first, this thing is goes up and close the first what we call first hole, the hole made by this red. So this blue, it will sort of like go in between the hole, so it will go there, and then this what we call this gray layer will cover the another hole, the one that we show before. It will cover another hole, the green hole there. So it will go and cover like that. So the slip plane in the gold is basically this 111 here. So the slip plane is normally exists in the most densest layer lah. So in this phase center cubic is this layer lah, the 111 layer. So coming back the thing, okay, I will end the thing. The reason why gold, the reason why gold is sort of like where is gold? Let me end this thing. Where is the thing? The reason why gold is softer than iron is because of this, the slip plane. And this slip plane is basically the plane where the what we call that have highest density. Okay, so that's why even though gold is denser than the iron, but the gold is softer due to the existence of the slip plane. It's much easier this plane in the gold to slip than in the iron. So I think that's it for today.